I want to connect this radius here with this, the length of the string, and like this angle that's up here at the top. Okay, so remember, these are all in a right angle triangle, right? This is the same length there, so what am I going to use? I'll just use trig. I've got the radius down here, theta's up there, this is opposite on hypotenuse, yes? So I'm going to say, but sine theta is equal to opposite on hypotenuse, yeah? Okay with that? So therefore, this is really nice because it sort of simplifies this dramatically in one hit, right? Therefore, the tension is equal to m r omega squared on r on L. I'll write that in brackets so it's very clear. You can see the r's will cancel, and what's going to happen to that L? It's just going to hop up into the numerator. So now you've got this. Is that okay? All right, lovely. So here's the tension in the string, right? Now I asked you all to get your string and to attach it. Now don't spin it just yet, okay? What I want you to, my goodness, okay, I'm going to stand back, okay? Now what I want you to notice as we do this, okay? The first thing I want you to do is just get your object, just get it rotating very slowly. Can you do that? Just get it rotating pretty slowly, okay? Now I want you to feel the tension in the string. Okay, can you feel it? It's pulling away from your fingers. Okay, if you let go, okay, yeah. Well, you need to attach it to something. Okay, because this is a light string. Yeah. Now, here's what I want you to notice. Don't do it just yet. Think about what happens at the moment. The mass of your object is not changing. The length of your string is not changing. But this is quite easy to change, right? This is quite easy to change. Now, if we were to, don't do it just yet. If we were to increase this, what would you predict would happen here? Now think about it, right? So okay, go ahead and make your thing spin faster. And can you feel the tension in the string? Okay? Now here's what's really interesting, right? Just stop it moving for a moment. If you just leave it there, right? It's stationary, so we've got Newton's first law, right? So you got gravity going that way, right? Weight force going that way, and you've got tension in the string going this way. They're exactly balanced, it's not moving. Okay? You can still feel that force. Okay? But now as you do it again, spin it up, and then feel what happens. Make sure you're secure, okay, as well. As you feel it going faster and faster, can you feel it wanting to break away? Okay? Now, remember, and you can slow it down again, and you're like, oh, okay, your fingers relax and what have you. Okay? Now I want you to remember when we were on, I'll just use this. When we were on the basketball courts. Remember this?
Was always like flying away from us.
Okay, now several times, right? You were doing this, and then what happened to your line?
It just expanded.
Your line just kind of broke apart, right? Why? Why did it break apart? What was it that made it break apart, right?
All the velocity was too high.
Yeah.
The angular velocity is so high that
Yep.
the maximum tension was
Fantastic. So you were holding yourselves together, right? Your angular velocity overcame the tension in the string, okay? And that's why you flew apart, okay? The thing couldn't, the body of the line of bodies couldn't hold itself together anymore, and so it broke. Okay, does that make sense? Okay, now just one more time. As you increase angular velocity, tension increases. That's no surprise. Okay, but there's something else that changes, right? As you increase angular velocity, you should find. Remember we said earlier there was no vertical movement, right? But if I spin it fast enough, there is vertical movement, right? What happens as omega increases?
Theta increases.
Theta gets bigger, right? Theta gets bigger, okay? Now, another way of saying, you can stop now, you can put that down. Another way of saying that theta gets bigger is that this height here, the perpendicular height of your object, your mass, from wherever the string is, that gets smaller, okay? So my question to you is, how can we show that this is the case? Not just like experientially, but how can we actually, demonstrate it?
To the L and the H.
Yeah, fantastic. So I've got this angle here, right? This guy's changing too, so I don't want to muck with that. I don't want to relate H to R because they're both changing. I would much prefer to relate h to L. Okay. Now, even though I'd prefer to do that, because I already have expressions for what all of these are, I can actually relate it to R. Watch this. Okay. Here's the thing I'm going to say. What about H? What about H? Okay. So I'm going to go after R because I already have R in a whole variety of spaces. So I'm going to say tan theta equals, what is tan theta? R upon H. It's fine, no dramas, okay. But remember I told you before, these two equations, they're going to be important. They're going to be important. Here's why I'm pulling out tan, right? That I got from the right angled triangle, okay? But these I got from my forces. Do you see tan? Do you see it there? I'm going to do 2 divided by 1, okay? So I'm going to say this is from just right angled trig, but 2 divided by 1, these two equations gives me, on the right hand side, t's cancel, sine theta and cos theta, that's tan. When I divide this by this, mass cancels, you get r omega squared on g. Yeah? So let's pull this over, okay? What I've got now is r on h equals r omega squared on g. What would you like me to do? Remember, I'm trying to understand h. I'm going to cancel the radius. So this is independent of the radius. That's interesting. And then you can see here, this is just 1 on h, right? So that means h is equal to?
Omega squared.
Omega squared. The way we would say this is that the height, that vertical distance there, is inversely proportional to the square of the angular velocity, right? Angular velocity goes up, height gets smaller, right? Which is why, do it one more time, just for the sake of it, right? Make sure you're secure. As you spin it faster, right, it has to go up. It has to go up, right? You're not pulling it up, it's going up because of this, okay? And of course, if you slow it down, decreasing omega is going to increase the height. Does that make sense? It's pretty freaking awesome, okay? Wow. All right, so that's the basic idea for the conical pendulum, okay? I want you to underline a couple of things with me. Can you underline this guy?
Everything's
Right?
underlined.
I underlined it all. This is the F equals ma of the conical pendulum. And I don't mean that figuratively. I mean it's literally the F equals ma. This is your acceleration over here. Okay? So if you see a conical pendulum diagram, it's a giveaway, right? This is your starting point.
So LW squared is A.
Yep. Okay?
So, is there any way to convert?
I'm not going to say, I'm trying to say bigger. It's really hard.
Maybe because I've seen a few questions where they ask you for
I have like
they give
a
you is there any way to convert into
Well, you convert tangential velocity to angular velocity, and then once you've got angular velocity, you can work out tension. Does that make sense? By the way, quick thing. You noticed I said, oh yeah, you know, you can't change the length of your string just spontaneously. Okay, you can't, but you can just, you know, wind it up and make it a bit shorter. Okay, now just think about this for a second. If the string is shorter, what does that mean?
tension will
It will experience less tension. It will experience less tension. Or if you maintain the same amount of tension and reduce the length, what happens to this?
increases.
It increases. Angular velocity increases. Now, we've all seen this before if you've ever seen the Winter Olympics and you see Olympic figure skaters, right? What they do is they're spinning, and then they pull in their body, right, which is effectively shortening the length of the string. And so because they've shortened that, this is going to stay the same. So angular velocity, it skyrockets and they just go woo like crazy, okay? They're taking advantage of this principle. Does it make sense?